It's great to be here, great to be back at LIDS. I was a student here many years ago and had a great time, and so I hope you're having a great time now too, and I look forward to talking with more of you through the day. So this talk is on exploration at scale, and it represents the culmination of work on exploration that's taken place over many years now, and it's work that I've contributed to, that I've worked with a number of these collaborators on, and that many other people in the community have contributed ideas to as well. To offer some background, around 2012, I started thinking that we really needed to figure out how to do exploration well, to do reinforcement learning well. And so I reviewed the literature on this and found myself quite dissatisfied with the existing approaches, especially in terms of scalability. It wasn't clear to me that there was a good roadmap to go from the ways people were thinking about exploration at the time to developing scalable systems that do exploration. And then around 2013, I recruited a few students. There's Zheng Wen, Ian Osmond, Dan Rousseau, to start brainstorming, and ideas started germinating here. When we worked on algorithms and theory for a number of years, Stanford provided a great environment for that. We made a lot of progress. And then, in a fortunate twist, DeepMind got very interested in this, and starting in around 2019, we did work with DeepMind, where we had substantial resources to build scalable systems to experiment with and implement some of these ideas. And generative AI came along, and we got involved with that starting around 2020, thinking about how the role that exploration should play in generative AI, the role that reinforcement learning and exploration should play in generative AI. And that leads me to 8 hours ago, when this paper was first published on arXiv on efficient exploration for large language models. Okay, so you're the first audience to hear about this. So most of the talk will be, or the first half of the talk will be about that, what's in that paper, and then I'll move on to something else that might be fun to discuss. So as I think people here are aware of at this point, generative AI operates by first learning from all the data it can grab from the web, plus maybe other repositories, and then it grows a big brain from that, so to speak, a base model. That model doesn't work very well, right? You don't have very good experience interacting with a pre-trained language model, but once you fine-tune it, typically involving a process where you gather human feedback, interacting with humans, then you get something that works really well, and then you get, something along the lines of ChatGPT. Okay, so you learn from the web, and then you learn from human interaction. Now, the role of human feedback in this process to date, I view as one of filtering. Basically, what happens is when you learn from all the content on the web, some of it's content that you'd like to emulate, and a lot of it's garbage. And so this process of learning from human feedback, as is done today, helps to quickly filter out large portions of internet content that should be classified as garbage. Okay, so that when you ask, how to treat, your COVID symptoms. It doesn't say, drink Clorox, right? That's taken out in this process of reinforcement learning from human feedback. Okay, now one way to think about this is, for each prompt in a generative AI, there's a space of possible responses it could generate. And you can think of the base model, the pre-trained model, as offering a prior distribution over what reasonable responses may be. Okay? Right. The role of this prior distribution is to steer you toward emulating things that appear more commonly on the web, or things that are similar to what would appear more commonly on the web. Okay, now the human feedback provides more information that allows you to offset this prior and deviate from what the prior would find most likely. And it's amazing that learning from passive human interaction, even with 100,000 interactions where you gather 1 bit of data per interaction, 100,000 bits, even then you get remarkable improvements in the quality of a large language model. Okay. Amazing. You train on terabytes of data from the web, but somehow 100 extra bits makes all the difference. All right, so the question I want to ask today is whether we can do more, whether we can do better by exploring efficiently rather than learning passively from human interaction, and also from the increases we're seeing in the volume of human data we're gathering, the volume of human feedback we're gathering. Okay, and I should mention that until now, this learning from human feedback has primarily been accomplished through interacting with hired raters, right? And the data is quite limited because of that, because it's an expensive process. But with the proliferation of chatbots, there's an accumulation of feedback coming in from users. For example, you get thumbs up and thumbs down data when you show users' responses. And so, there's this huge opportunity to leverage more and more feedback to see how far we can take generative AI. All right, and let me speculate that, the role of learning from human feedback is going to go from one where it's about filtering garbage from the internet to one where it's about generating greater ingenuity in these large language models. Okay. So in particular, with so much human feedback, you might imagine being able to deviate more dramatically from what this prior distribution induced by pre-training suggests. Okay. And the picture is, as you interact with humans, maybe a chatbot can generate millions or billions of somewhat innovative responses, experimenting, right? And maybe one of those turns out to be ingenious. And so it realizes that from the human feedback. And then it takes the next step. It starts generating further deviations based on that. And so in this process, you could imagine content emerging that you would never have imagined to see based on emulating the internet. Yeah. All right, so you can imagine something coming out of the chatbot, doesn't know whether it's any good or not, but a human says, yeah, that's a great idea. Okay. And it's plausible that this can lead to things that are much better than what humans can generate. Now, how could that be? All of the data is coming from humans, right? First, there's the internet data, and then there's this data from human feedback. How can a chatbot learn to generate stuff way better than humans when it's only learning from humans? Well, I think that's plausible, partly because verification is much easier than synthesis. And this is analogous to the concept of NP completeness. where there are problems where it's very difficult to generate a good solution, but it's very easy to say that a solution is good when you see the solution. Yeah. Okay, so my conjecture is that this growing data and efficient exploration will help pave the way to superhuman ingenuity. And this goes back to the roots of reinforcement learning. Right? So one of the early pioneers in reinforcement learning was Clough. And he used to raise eyebrows by saying things like this. So other learning paradigms are about minimization, while reinforcement learning is different because it's about maximization. Okay, so you might laugh at that, but it's actually quite deep. Because at the time, there were other learning paradigms that were based more on emulation or on defining. So if you take something like adaptive control, for example, the mindset in adaptive control is to prescribe a trajectory that you want the system to follow. And then you want to minimize how far you deviate from that trajectory. Right? It's a minimization problem. Right? And reinforcement learning started with this mindset where you don't know how far you can go. The sky's the limit. Who knows how good a system can get, right? There's no notion of minimizing error and going down to zero because I don't know what may come out of this, and so superhuman ingenuity fits in that mindset, which differs from the mindset of emulation or target tracking. All right, so what this paper is a first stab at demonstrating benefits of efficient exploration in large language models. And so what do? Well, we use a standard generative AI interface for learning from raters. And what this involves is you have a system where for each prompt, and in this particular experiment, we sample prompts from a publicly available data set produced by Anthropic of prompts. Sample prompts from the Anthropic data set. And we have a system that for each prompt generates a pair of responses. And then humans, but in this experiment, we don't actually use real humans. We're going to use simulated humans, simulated using a simulation system that is used at Google. We simulate what a human would choose between these two responses. Either it says it likes response 1 or response 2 better, and it sends that preference data back to the system. Okay. And so here's the system, and we're going to constrain the system design so that we have a simple experiment. And the way we constrain the system design is we're using the Gemini model. There's 4 sizes of Gemini models. Here we're going to talk about using the simplest Gemini model. It's a large language model produced by Google called Gemini Nano. And so you take Gemini Nano, you take the prompt, you generate a bunch of responses, say 100, using the base language model. And then you have some exploration scheme that decides which 2 of these 100 to show the human. Okay? And then the human says which one it likes better, which one they like better. And then we train some model based on the human feedback. And that model informs the exploration scheme so that for the next prompt, the exploration scheme can have a different way of choosing from among these 100 responses. Okay, it's a very simple architecture and interface. And so the game here is in designing how this model is learned and how pairs of responses are chosen to event. Okay, So that's the setup of the experiment. And then, when you compare different algorithms, you need some way of scoring each. And the way we do that is we assess the win rate relative to the Gemini Nano model. So again, you take sample anthropic prompts from an out-of-sample. This is an in-sample set, we call it. This is an out-of-sample set. From an out-of-sample set, you sample prompts. You feed it to the Gemini Nano model. You feed it to a model like this, where you sample 100 responses from Gemini Nano, and then take the best one according to your reward model. Okay? And then you show both responses to a human rater, and then you see the preference. And so what we do is we assess the win rate, in particular how many times this best of n model that we've produced wins over the response generated by the Gemini Nano model. Okay? So that's how we're going to score models. All right, so that's our setup, and here's what we found. So let me explain this. On the vertical axis here, I've plotted queries required by double Thompson sampling. Okay, so double Thompson sampling is a very simple algorithm. You give it 100 responses. Okay. Oh, the double Thompson sampling is an algorithm that leverages a model with uncertainty estimates, right? Estimates of model uncertainty or epistemic uncertainty. So what happens is you give it 100 responses, and it samples a model, a point estimate model from the posterior distribution given by your uncertainty estimates, from the from the posterior distribution of our models that you're representing. And then you choose out of the 100 the one that optimizes that sample. Okay. And for the second response, you do the same. But if there's a collision, if you get the same response twice, you do this again. You keep doing it until you don't get a collision. Okay, when you have two distinct responses from double Thompson sampling, you send those to the rater. Okay, so that's double Thompson sampling algorithm. And I have this on the vertical axis because it was the algorithm that worked best among those we experimented with. All right, the other three here are passive exploration. Now, passive exploration sounds really dumb, but this is what's done right now in RLHF systems. People do passive exploration. What's passive exploration? You have the Gemini, the base model, right? Sample two responses. You send those to the human, and you get the feedback, and that's it. So you don't worry about being strategic about exploration at all. You just, passively show humans pairs of distinct responses and learn from the feedback. Okay. Then there's Boltzmann exploration. Boltzmann exploration uses a point estimate reward model. So it needs a model that sort of says, I think this response is better than that response. And Boltzmann exploration sort of biases its selection of responses towards the better ones. Okay, and there's hyperparameters controlling how much you bias things in that direction. And so you can use Boltzmann exploration to select pairs of responses for human feedback. And what's Infomax? Infomax uses uncertainty estimates, and it's maybe the first kind of algorithm that comes to people's minds when they think about exploration using uncertainty estimates. What you try to do there is you try to choose a pair of responses such that the feedback will offer you the maximum information gain. Okay? All right, so here are the results. So on the vertical axis, I have the queries required by double Thompson sampling, which was our winner. And on the vertical axis, I have the queries required by these alternatives to generate the same win rate. Okay, how many queries do you need by a competing algorithm to generate the same win rate? And so if I had double Thompson sampling on this axis, you'd just see a 45-degree line because it'd be the same algorithm. But for these other algorithms, just see these things shoot off. Right? This is what's being done right now, passive exploration, the blue curve. Okay. See, so it seems like huge gains. So when you around 3,000 for around 3,000 queries made by passive exploration, double Thompson sampling seems to match that with about 300 queries. Okay, so a few observations here. One is uncertainty estimation seems to play a critical role. We experimented with many algorithms that just use a point estimate reward model, and Boltzmann was the best we could find. Boltzmann exploration was the best we could find. And as you can see, that fared far worse than double Thompson sampling. Okay, so uncertainty is playing a critical role here. And the issue is, uncertainty estimation conceptually is something very simple. All you have to do is Bayesian inference. But doing this at scale with large neural networks, requires different algorithms. And we've been working on that for the past few years at DeepMind and have developed these tools we call epistemic neural networks for doing this. So that's what we've done, that's what we've leveraged in these experiments. And then the other thing that's interesting is that the choice of exploration algorithm can be critical. So I was surprised by this, but double Thompson sampling for some reason in this experiment works much better than InfoMax. Now, if I had to speculate on a reason why double Thompson sampling is working much better than InfoMax here, is that InfoMax may be trying to acquire a lot of information that's actually not that useful for choosing good responses. Okay, so it may be wasting its exploration on learning things it doesn't really need. Okay, whereas double Thompson sampling, because of the way the algorithm works, tends to focus on comparing responses that are serious contenders. Okay? All right. The other interesting observation is that the percentage benefit of efficient exploration grows with scale. In particular, these curves seem to be convex. And so as you scale the number of queries, it seems like the percentage reduction you get from using efficient exploration gets larger and larger. Okay, and so this is very promising. And I'm thinking this can potentially lead us to superhuman ingenuity decades earlier than otherwise, though a huge amount of research remains to be done in this area. Okay. Now, I don't really have time to talk about all the different areas of research that I think remain as challenges, but let me just name one issue as an example. Here's an example of an outstanding issue. Right, these are actually the same results as in the previous plot, but plotted a different way. Here I've plotted the number of queries versus the win rate delivered by these different algorithms. Okay? And one thing is, these algorithms seem to converge. And these algorithms are sort of designed to converge. Like that's the mindset in the way neural networks are trained, and that's a mindset in regret analysis of exploration algorithms, to sort of get these things to converge quickly. But what we really want is, to leverage 1 million times more data than this and have things keep improving. Right? So why do we get convergence like this? Well, one is because of the way the algorithms are set up. Another is because of model capacity. Like we're using a neural network of a particular size that was sort of sized right for the amount of feedback we're gathering in this problem. And so there's lots of things that are built in here to get this kind of convergence. But what we really want is a methodology that keeps learning and keeps growing and keeps getting better. Along those lines, there's an area called continual learning that is thinking through these issues of how to get neural network learning and more broadly reinforcement learning to work in this mode where you keep learning more and more over time. And we sort of did a literature review and some early thinking about this area and wrote this monograph last year based on that. Okay, but there's many other outstanding issues. It's a lot of work to be done to work out how to get from here to the point where we can reliably support superhuman ingenuity. Okay. Now, I was thinking of talking about a combination of that and all the theoretical and foundational research over the years that led up to this point. But then I thought, gosh, thinking back to when I was a LIDS student, that wouldn't have been the most fun experience in a talk. In particular, some of you in the audience I know are already real experts in this area, right? So when I talk about this theoretical work, this is going to be the reaction. I already know that, right? And then for people who aren't experts in this area, it's going to be kind of overwhelming and too much, right? And so it's not going to be fun for you. So then I thought, I just thought about this last night. What should I talk about? Well, let me talk about something that is really, fresh in my mind, where I don't really know much yet in terms of what the answers are, and it's a very LID style thing, and that might be fun to engage you with, and something people will enjoy thinking about. So let me talk about scalable crowdsourcing, which is a subject I've been interested in over the past year. It's a less mature subject, and actually the first paper I wrote with some students at Stanford was just done 1 week ago. Okay, and I think this is a great area for LIDS style thought, as you'll see. So what's crowdsourcing? Well, over the past few decades, people have come to realize that by querying many people and getting opinions, somehow you can aggregate them to produce results that are much better than individuals can. Okay, and interest in this area really took off in 2005 when Mechanical Turk was launched. And this is a graph of citations of Mechanical Turk from the academic literature post-2005, right? Okay. And these are three very interesting books on different aspects of crowdsourcing and why and how it can be helpful. But here's the crowdsourcing application of our time, right? You have an AI, and the AI needs to interact with people to learn from them how to do better. Okay, and the interface I discussed in the part of the talk on exploration is an example of this. You send a person a prompt and 2 responses, and they say, I like response 2 better, right? And the AI benefits a lot from this feedback. Now, one feature of these systems today is that the input from each crowd worker is weighted equally. Okay, so everybody's treated the same. And so a question that arises is, can we do better by weighting different crowd workers differently? Okay. Now, this actually isn't a new subject. People have been thinking about this for a long time. But the systems today don't use any of that. Right? They just weight everybody equally. So I'll discuss and speculate on why that's the case. Okay? But to digest what I'm talking about here, it's helpful to have a LID-style toy model. So this is the kind of thing, I'd go into John Sissiklis' office when I was a student and draw on the whiteboard to start thinking about a problem. Okay, so here's a LID-style model. Let's say we have some unobserved outcome ZT, just a real number, and you have a bunch of crowd workers, crowd worker 1 through K. Each of them generates an estimate of ZT. We'll call it YT1 to YTK. And then a center takes the crowd worker estimates and produces a group estimate, Z hat T. Okay, we do this at each time step. Okay, now that is a LIDS style model. Okay, and to be a bit more formal, suppose there's actually an infinite number of crowd workers out there. K goes from 1 to infinity. But the center that has to generate the group estimate only observes the first K. Okay, suppose the outcome is a normal random variable, 0 with variance v. We don't know what it is. That's our belief about it. And the estimates are each zt perturbed by noise, delta tk. And let's say the noise is generated by a factor model with an infinite number of factors. Okay, so ckn is the loading of the nth factor in generating the estimate of crowd worker k, and xtn is the shock, the factor shock for the nth factor. Okay, so the shocks are common across crowd workers, but the loadings are different for each crowd worker. Okay, and if we want to weight the crowd worker estimates, to get a group estimate, we say z hat t is equal to theta t transpose yt. Yt is a vector that has k dimensions, 1 per observed crowd worker. And we observe the same crowd workers in every time step. Let's say those are the crowd workers on our payroll. All right, and if you go with equal weighting, well, what's equal weighting? Well, you multiply each crowd worker's estimate by the same number, and then you add them up. Okay, so you weight each crowd worker the same, and you can have some hyperparameter. I didn't mean this to be the same v, but you can have some hyperparameter that you use to regularize how you aggregate these estimates. Okay, but you weight everybody the same. Okay, so can we benefit from unequal weighting? Well, yes. So if you interact with the same crowd workers over time, you can learn these factor loadings. Right? And once you learn the factor loadings, you can use that to come up with weights that are better than uniform. Okay, and here's what you get with the model I defined in the previous slide. So you could look at the number of workers required if you weight each crowd worker the same, and then you can ask, well, how many crowd workers would I need if I came up with better weights after learning for a long time from interacting with the same crowd workers? And you need far fewer. The clairvoyant is where you've learned from many time steps. After learning from many time steps, you need far fewer crowd workers. So rather than 100 crowd workers to get a particular mean squared error in your group estimates, we have like 19 crowd workers here. All right. Okay, so why do we have this blue curve? So this blue curve represents what we call the only skilled clairvoyant, where you take the factor model and you ignore the correlations implied by the factor model, but just use the noise variance for each crowd worker, right? So the point here is using the covariances between crowd workers plays an important part of an important role in the benefit you're getting from learning. Okay, but the message here is you can do much better than equal weighting in this model. Okay, now this is not new. There's a large number of papers that have considered models for doing unequal weighting and have said, you can benefit from this. Okay, now they aren't all our factor linear model. There's different kinds of models. There's Bayesian networks, there's all sorts of things, and they all show benefit, and so it's very similar to the narrative I just articulated. But you got to ask, why is none of this used, right? AI is an area of huge investment. They're paying a lot to get crowdsourced data. Why aren't they trying to do better? Well, there's this interesting paper that suggests that misspecification is the issue. And what this paper shows is that if you take one of these models that allows you to get better weights, right, and you apply it to data that is not consistent with that model, you actually do much worse than equal weighting. Okay, so if I take my factor model, for example, there's no saying that that's how the data is generated. If I try to apply weights based on interpreting data as being generated by that factor model, right, I'm probably going to get much worse results than I would by just assigning equal weights. That's the issue. Okay? Okay, so the question is, how do we deal with this? How can we get some benefit from huge numbers of interactions with crowd workers that allows us to come up with weights that are better than uniform and that will really work? Okay, and this is actually one of the themes and one of the triumphs of neural networks. So neural networks have served us well as a tool for avoiding misspecification and just letting the data talk. Right? When you use a huge neural network, right, you're not going to misspecify so much because you could fit almost anything. Now, traditionally, people would think, oh yeah, but then you're going to overfit the data. But what we found is, you don't overfit the data. These neural networks, even when you train them on little data, do reasonable things. There's some implicit regularization going on. Okay? So we're going to bring neural networks to the rescue here in dealing with this misspecification issue. All right, and so we have this new algorithm that we just that's in this paper, but we haven't really studied much yet, and we haven't really established as one that really works. But it's fun to think about, and I suspect many modifications will come to this sort of algorithm from great minds like those in this room. So let me tell you about where we're at with this. Okay, step one in this algorithm, which we call predict each worker, is to fit a masked autoencoder, which is a neural network. It could be a big neural network where the goal is to learn about the crowd worker skills and dependencies, how their estimates tend to relate to each other. Okay, so the idea is, suppose you have 5 crowd workers. Then you fit a masked autoencoder so that you take inputs from those 5 crowd workers, and the outputs are predictions of what each crowd worker would produce. So the predictions are not y1 to y5, but p1 to p5, because I'm talking about distributional predictions. Right? Each prediction is a distribution that represents what I think y1 should be. Now, if I'm giving y1 as input, what does it mean to be predicting y1 as output? Well, the way the masked autoencoder works is when you train, you hide one of the crowd workers and you predict, and you fit the model to predict that crowd worker's input given only the inputs of the other crowd workers. Okay, so in the end, you can leave any crowd worker out and predict that crowd worker's estimate based on the others. Okay, so we fit these this masked autoencoder. Okay, so you get this masked autoencoder, then what do you do? What do you do with a masked autoencoder? Like, how do I get my weights from that to assign to the different crowd workers? Well, here's a formula. You take the mean of each prediction. So what do I mean by the mean of each prediction? Well, okay, so you have a bunch of crowd workers that give you their estimates. You leave one out. You predict what that one should have been based on the other crowd worker estimates. You take the mean of that distribution and you take the variance of that distribution. Okay? Then you plug it into this formula. Okay, what does this formula say? This formula says I take 1 minus the sum of the gradients of the mean of the estimated crowd worker k the gradient of that with respect to the inputs of the other crowd workers. Okay, so I sum those up, 1 minus that, divide by the variance. And then I have a hyperparameter v, right, which I can tune. Okay, that's the algorithm. Now I'll give you some motivation. So first for the neural network architecture, this was really motivated by Gibbs sampling, right? The fact that Gibbs sampling works, right? That it can be used to generate the any distribution using these leave one out conditional distributions, right? That motivates why a masked autoencoder, if you learn it, ought to express all information you need about the crowd workers. Okay, what motivates the aggregation weights? Well, this came out of our intuition. We started thinking, gosh, each crowd worker weight should increase with its predictability. So if a crowd worker is perfectly predictable, we don't want to give it any weight. It's already expressed by the other crowd workers. And the second is that the weight should decrease with how sensitive the crowd worker is to other crowd workers, right? That correlation should, I'm sorry, I misspoke on the first one. If the crowd work is predictable, you want to give it a lot of weight because that means it's not noisy. That crowd worker really knows what it's doing because it's always representative of what all the other crowd workers would want to do. Okay, but the weight should decrease as a crowd worker becomes sensitive to other crowd workers, right? Because that shows correlation. You don't want to overcount information. Okay, and then we started thinking about this, and lo and behold, that formula that we intuited turns out to be optimal for a simple case. So if the data is generated by a linear Gaussian factor model along the lines of what I presented earlier, and the masked autoencoder is a simple one where it's essentially doing a Bayesian linear regression, right? Then this thing's guaranteed to give you the optimal crowd worker weights. Okay, so that serves as some sanity check, right? But I think this subject is still in its infancy. A lot of thought required to understand how this scales, how this works with complex nonlinear models, etc. Right? So the algorithm and the formulas could be applied broadly, but as we apply them more broadly, we might learn stuff and want to change them. Okay, so let me close with some thoughts. So on LIDS style research, one is I think it's great for, in fact, ideal. This is the style you guys have here is ideal for ideation and generating deep understanding. Yeah. And I think this sort of work can, and in fact is essential and still essential to generating transformative innovations. But the path to real world impact can take a long time for this kind of work. It can take a long time. And a couple of things that I've learned are very helpful post my LIDS experience is that understanding the applications helps a lot, and interacting with systems builders helps a lot. And if you're missing those, on this long path of modeling and ideation, right, to impact, it's hard to steer yourself to get to the destination in a reasonable time frame. And my final remark is, we all miss Sanjay. Okay, thank you.